Before I begin, let me clarify that I'm not claiming you'll become a nuclear physicist in 10 minutes. Most of you probably don't want to do that anyway. It's not for everyone. But if you want to understand what I believe are the most important and essential concepts in nuclear physics, then stick around because I'm about to make you dangerously interesting at your next dinner party. And that's about to happen right now. Before we start, I want to acknowledge the inspiration for this video, which comes courtesy of today's sponsor, Magellan TV. It's where I saw a documentary called North Korea versus USA, a nuclear chicken game. It's a fascinating story of how the Kim dynasty of North Korea has been working on becoming a nuclear power for over 60 years, during which time the US has gone through 13 presidents with different policies, and how this proved to be a big advantage for North Korea. It got me thinking about nuclear physics in general. This is just one of thousands of high-quality documentaries on Magellan TV, the highest-rated documentary streaming app on Google Play, and they add more than 20 hours of new content weekly. Magellan has a special offer for Arvin Nash viewers. Right now, your first month is absolutely free. Just click the link in the description and start enjoying the highest-quality documentaries available, including free 4K videos and never any ads. And you'll be supporting our channel when you sign up, so I can't thank you enough for that. Now, back to the show. Atoms are made of a positively charged nucleus surrounded by negatively charged electrons. The nuclei of atoms are made up of protons and neutrons. These are called nucleons. Because all the protons have the same charge and like charges repel, force can be calculated using the classical Coulomb's law equation here. You can see that the force between charged particles is inversely proportional to the distance between them, r. Because positively charged protons are in such close proximity to each other in the nucleus, the electrostatic repulsive force between them is enormous. Two protons typically separated by the width of a neutron is on the order of 60 newtons, or 12 pounds. But what keeps them together against this tremendous repulsion is an even stronger force called the strong nuclear force, which is about 100 times stronger than electromagnetism. This force comes from one of the four fundamental forces in the universe, the strong force. But this force, unlike gravity and electromagnetism, operates at very small distances, only about the width of a proton. And it only operates within and between protons and neutrons. Electrons, photons, and neutrinos are not affected by it. You can think of the strong force like Velcro. When two objects carrying the strong force are very close, they stick to each other like glue. But if they're far apart, they are unaffected. This means that a nucleus can only grow so large. The reason is that the two opposing forces, electromagnetism and the strong force, operate differently. The strong force only acts at short distances, so a given proton or neutron's attractive effect diminishes rapidly as the nucleus grows larger. But since electromagnetism has an infinite range, its force accumulates as more and more protons are added together. So all the protons in a nucleus participate in repelling each other. This repulsion quickly overwhelms the attractive effect of the strong force as more protons are added, disrupting the stability of the nucleus. So the heaviest stable element is lead, which has 82 protons. The number of protons in an element is important because it is solely responsible for its atomic properties. This proton number corresponds to the position of the element on the periodic table. A given element or atom can have the same number of protons, but different numbers of neutrons. These are called isotopes of the element. They have exactly the same physical and chemical properties, but differ in mass. Stable nuclei consist of roughly the same number of protons and neutrons. The neutrons serve to provide additional strong force needed to keep the nucleus stable. Without neutrons, not even two protons can be held together against their repulsion. Free protons are stable, but free neutrons are not stable. Lone neutrons decay into a proton, an electron, and an antineutrino within about 15 minutes. But inside the nucleus, they remain stable because it is energetically unfavorable for them to decay. In other words, the energy gained from a neutron decaying to a proton is lower than the increased energy required to keep an additional proton in the nucleus, if there are plenty of other protons around. But this type of neutron decay in the nucleus is not impossible and can happen in very neutron-rich isotopes of a given element. But a nucleus cannot have too few neutrons, or the nucleus will not be stable. It also cannot have too many neutrons because eventually the strong force can no longer keep them from decaying into a proton and forming a different element. Protons and neutrons, just like all quantum objects, are subject to the laws of quantum mechanics. One consequence of this is that quantum particles have a very small but non-zero probability of appearing anywhere in the universe. The reason I mention this is because it is tied to a certain kind of natural radioactivity called alpha decay. If a nucleus is very large or has an excess number of protons and neutrons, and the strong force can barely hold it together, quantum objects have a higher probability of appearing on the other side of an energy barrier if the barrier is not very high. In the case of very large nuclei, such as uranium, the energy needed to liberate protons and neutrons is small enough that sooner or later an alpha particle, which is essentially a helium nucleus consisting of 2 protons and 2 neutrons, can quantum mechanically tunnel through the strong force barrier and appear outside the nucleus. Then they speed away very fast. This is what we call radioactivity. If you want to learn more about quantum tunneling, I have a video on that right up here. There are 3 forms of natural radioactivity: alpha, beta, and gamma decay. An alpha particle consists of 2 protons and 2 neutrons. This type of radiation happens via the mechanism I just described. The beta particle is a high-energy electron. In some very large nuclei that might be barely bound together, a second fundamental force called the weak force can compete with the strong force and cause a neutron to decay even though it's in the presence of protons. As I said before, when a neutron decays to a proton, it gives off an electron and an antineutrino. This electron that it gives off is the beta particle. A gamma particle is a high-energy photon, also called a gamma ray. Gamma rays are usually emitted by excited nuclei that have been created after either an alpha or beta decay. The reason these processes release such high-energy photons is because they involve nuclear processes which are due to the strong force. And since the strong force is so much stronger than, for example, the next strongest force, electromagnetism, whenever there's a shift to lower energy levels within the nucleus, an enormous amount of energy is released. And this high energy is in the form of gamma rays. The 3 forms of radioactivity have very different abilities to penetrate matter. Alpha particles can be stopped by a thin piece of paper. Beta particles can penetrate your skin, but can be stopped by a thin sheet of metal, like aluminum foil. But gamma rays are very difficult to stop and can penetrate through even an inch of lead. Why is this the case? Alpha particles consisting of 2 protons and 2 neutrons are relatively big, heavy, and thus slow. Because of their large size, they can be easily blocked. Beta particles travel much faster and can penetrate matter more easily because of their higher velocity and smaller size. Gamma rays have no charge and they're moving at the speed of light. These photons pretty much have to hit a nucleus directly to be stopped. Alpha and beta decay change the atomic identity of the decaying nucleus because they change the number of protons. Alpha decay subtracts 2 protons, so the element moves down 2 notches on the periodic table. Beta decay changes a neutron into a proton or vice versa, so it changes the type of element either up or down. A radioactive nucleus is characterized by something called its half-life. What this means is that if I have a certain number of radioactive atoms, let's say 16 atoms, and its half-life is 1 week, then 1 week later I'll have half of this, or 8 atoms remaining. And in 2 weeks I'll have half of that, or 4 of the original atoms left. And this goes on. Half-life is a statistical concept. If you're holding the 16 atoms, you'll not be able to determine which of the atoms will decay 1 week from now or 1 billion weeks from now. You can only say that any given atom has a 50-50 chance of doing so in the time of 1 week. If a large nucleus, like some isotopes of uranium like U-235, is hit by a particle, usually a neutron, then it will be split into 2 smaller nuclei. This is called nuclear fission. If the total mass of the 2 smaller nuclei is less than that of the uranium before it was hit, the missing mass is turned into energy via the equation E equals mc squared. In the case of certain isotopes of uranium and plutonium, such as U-235 and plutonium-239, when these are hit by a neutron, they split into 2 lower mass nuclei and 3 neutrons are also thrown off. If there's enough fissionable nuclei in high enough concentrations, then it is possible for the 3 thrown off neutrons to in turn fission 3 more nuclei, which in turn fission 9 more nuclei, which in turn fission 27 more nuclei, creating what's called a chain reaction. This is the mechanism behind the atomic bombs dropped on Hiroshima and Nagasaki during World War II. A kind of opposite of fission is fusion. This happens when 2 small nuclei, such as hydrogen, which consists of only a single proton, can be brought close enough together that they fuse into a single nucleus. Fusion is very difficult to achieve because the protons strongly repel each other. Only gases heated to millions of degrees Celsius have atoms moving fast enough so that they can approach each other close enough to achieve fusion. Quantum tunneling also plays a role here. A hydrogen bomb achieves very high levels of energy release by using the heat of a fission bomb to trigger hydrogen fusion. I have a video on how a hydrogen bomb works if you want to learn more about it. The sun is powered by hydrogen fusion, but its mechanism is quite different than that of a hydrogen bomb. It does not need nearly as high a temperature because its mass creates tremendous pressure in its core, pushing hydrogen nuclei together. The sun has such a huge amount of hydrogen atoms that the low probability of fusion still amounts to a very high number of nuclei fusing together. Now, if you've seen this whole video, I officially crown you a dangerously interesting nuclear physics aficionado. Please use your newfound powers for good and not for evil. I'll see you in the next video, my friend.